Good morning, everyone. I'm Audrey Washington. I'm a second-year PhD student here at Caltech in the Cushing Group in the Department of Chemistry and Chemical Engineering. And today I'll be talking about an instrument that we're developing in our lab, which is an ultrafast electron pump and EELS, or electron energy loss probe, to reveal specialized dynamics. And so yeah, let's get right into it. So I said a lot of words there, and let's focus on the ultrafast part. So what is ultrafast spectroscopy? And ultrafast spectroscopy essentially is when you have two pulses. You have the first pulse, which is called your pump, and you have a second pulse, which is called your probe. And the separation in time between these pump and probe pulses is of the order of femtoseconds. And a femtosecond is 1 × 10⁻⁻15 seconds, which is approximately how a femtosecond is to 1 second. 1 second is to 31.7 million years. And to put that into some perspective, that's about half the time since the dinosaurs went extinct. So it's very, very fast processes that we're looking at here. So what are processes that happen at these ultrafast timescales? Of those processes, we mainly are looking at solid-state materials, but we could also look at reaction dynamics. But looking at the solid-state picture, we have a nucleus that is exciting core-level electrons to the outer shell valence electrons, and that would happen on the order of femtoseconds. We also have photons, which are oscillations of your lattice, and those oscillations have particular modes, and those oscillations also last and are excited and decay over time in the order of femtoseconds. And lastly, we also have plasmons, which are like photons, but instead of looking at the full lattice, we're looking at mainly the electron bath and how those electrons are oscillating, and those form and decay also on the order of femtoseconds. So that's just a glimmer of what the femtosecond scale can tell us. There's also other quasi-particles like excitons, or coupled between these particles like electron-photon coupling. So this is just a small picture, but it gives us an idea of why this is important. So what does our spectrometer look like? So this is the kind of behemoth that we're working with here. So I'm gonna kind of just walk through the full path with you. So we start out of our laser. So the laser is right about here. And our laser is a 1035 nanometer laser, and that's a pulse laser, which means that we can have electron packets not electron packets, but photon packets sent at pulse rates. And the pulse rate for our laser is from single shot to 50 megahertz, but the separation in time between those pulses is 300 femtoseconds. And so we're sending that 1035 nanometer, which is the wavelength of light coming out of the laser, and we're sending that through a 50-50 beam splitter, which splits the beam in half to our pump and our probe. And our pump goes through a delay stage so that we can have a set group of mirrors set back in space so that we can delay the time between the two pump and probe pulses so that they're very, very close in time to each other, and we can get to specific timescales that we're trying to look at. And then once we send that pump and that probe through the delay stage, we also have the THG. So THG stands for third harmonic generation, which means we upconvert our 1035 nanometer laser to a 517 nanometer and then to a 343 nanometer light. And essentially that just means we have higher energy beam instead of the initial 1035 nanometer beam. And I'll get into why it's important to have a higher energy, but we do the third harmonic generation, and then we send that into our low energy electron gun. So our low energy electron gun has a lanthanum borate photocathode that is giving us energies from 1 to 1,000 eV. And we want the low energy because the low energy allows us to implant our electrons into our sample, and that can excite the system. Or it can move the electrons around in the system, and that allows us to later record with our high energy gun, which is on the order of 1 to 30 keV. And that we need a higher energy because the larger energy that we implant into our system to probe, that allows us to reach any energy measurement less than that, which I'll also talk about more later. But yeah, so we send these 2 electron packets into our detector, and then our detector allows us to separate our energy of our beam. So we have a positive side, which is in the center, and a negative side, and that allows us to spread in energy. Okay. So what is EELS? So EELS is, like I said, electron energy loss spectroscopy, where you send in your electron beam, and that electron beam loses some energy, and we record the energy losses, and that tells us how it interacted with our sample. So we have 2 types of scattering that occurs when the electrons interact with the sample. We have elastic scattering, and we have inelastic scattering. Elastic scattering, essentially we lose no energy in that case, and we only have a momentum loss. And then in inelastic scattering, we have a energy and momentum loss. And so if you interact inelastically with the atom, at the core level, you lose higher energies, while on the valence level, you lose lower energies. And that could give us either element-specific information or even plasmonic stuff that I was talking about earlier, which is on more the outside of your atom. And so the most important part of our setup, in the full crux of it all really, is our electron pump. So the electron pump is very exciting because we're allowed to now excite through momentum states. So in the picture on the top left, we have a blue arrow that goes up, and that's supposed to represent a typical photon that's exciting a system. But if you use an electron to excite a system, you can excite through momentum space, essentially allowing us to access more excitations with less energy, which has not been accessed before. And that will give us way more interesting dynamics that can tell us really how a real system would work, because the actual way atoms interact with each other is through electrons and not photons exciting that system. Additionally, electrons have mass, like I said, which means they have momentum, and that means that electrons require less energy to excite the same system, and so we don't need super high energy photons to look at these momentum excited systems. Okay. And so how are we generating these electron packets? We're generating these electron packets by sending a 343 nanometer laser. And why we need the 343 nanometer laser is because the work function of our photocathode that generates our electrons is 2.5 eV, or about 500 nanometers. So we have a higher energy laser than 500 nanometers to allow us to send out electron packets. We then have our one-millionth grid that allows us to select what energies we're sending out of our photocathode. And then we have a focal lens that allows us to focus our beam and choose the beam size of our pump. And then we also have a deflecting lens that's allowing us to choose the position of where the beam is hitting on our sample. And so this is generated through photo excitation, where you have an electron from the photocathode excites, and then it gets sent over into vacuum once it reaches over the work function. And typically we generate that through thermionic emission or electrostatic emission, but photo excitation allows us to have the pulsing packets that I was mentioning earlier to reach the ultrafast regime. Otherwise, we wouldn't be able to look at the ultrafast dynamics that we see in our spectra. So additionally, the design of our chamber allows us to have multiple geometries. So we're not limited to just one type of excitation. We're also allowed to look at different positions within the sample to give us different information. So in this picture, we have on the far left transmission, where you send in the pump into your sample, and then you probe through the sample, which allows us to look at the bulk of the material, or the core losses, or anything element specific. And then we also have reflection, which allows us to look at the surface level. And so we're exciting into our sample, and then we send the probe so that it hits the surface and comes off of it, and that gives us more like plasmonic or phononic sensitivity. And then finally, we have our aloof geometry, that allows us to look purely at the surface plasmons, so what's happening with the electrons on the very surface of our sample. And so we're selectively looking at all of these things through the different geometries. And finally, we can also not just have electron packets, even though they're very, very interesting. We can also have optical pumps or optical probes, so a photon, so we can compare traditional spectrums to our electron or electrically pumped system. So yeah, that's all great and dandy, but like, what are we trying to measure here? Why are we building an instrument like this? So we can look at solid state materials and how, again, like their photons or plasmons are moving over time. And we can also look at reaction kinetics and reaction dynamics and how maybe like CO2 in the atmosphere is dissociating and what the timescales of that is and what the exact mechanisms of that would be. And we can also combine these systems if we want to really look at the multi-phase interfaces, and we can look at a solid exciting some gas and see how the electrons transfer within that system. So yeah, that's kind of how we want to move with this project in the future. Here is an image of our setup over time and how it's been developed, and you can see it's a very big room and a big vacuum chamber. And so we are adding our laser table here, and eventually we'll get to a point of combining the two and exciting our electron beams and seeing how those interact with our samples and revealing dynamics that had not been seen before, because we're typically exciting with photons. So yeah. Yeah, that's the current setup, and I'd like to thank the Cushing Group for all of their guidance and help, and also Nicholas, Heller, and Bethany for being great mentors, and here are our funding sources. Thank you.